Good afternoon, everybody. Hello. Hello. All right, so thank you for coming on a Friday post-exam. I know that's always a little stressful, but you're here, so that's great. I'll try to reward you with a couple demos, but there's a lot of material to get through, so you'll need to buckle it in and make sure that you're staying with me, staying on top of this rotational stuff. If you think back to the beginning of the semester, we talked about how objects move when they accelerate and have certain velocities and enough time passes and so on. Those were our kinematics equations in the linear picture. And then we studied why. Why would they accelerate? And for that, we needed Newton's laws and we needed a notion of forces and so on. So we can do the same thing with the rotational picture. We've already talked a little bit about how things might rotate when they have angular acceleration and angular velocity. And so now the question is that we're going to answer today is why? What gives them some sort of angular acceleration? In other words, what I want to know is there an analog to Newton's second law, but for rotation, right? So we had that the net force equaled mass times acceleration in the linear picture. And so in the angular picture, there should be some cause for angular acceleration. You might anticipate that the acceleration we're going to plug into this analogous equation is going to be alpha instead of a, right? Angular acceleration instead of linear acceleration. But then the question is, what's the analog to mass? Mass is a pretty fundamental thing. It's about how much matter something is made up of. So what could be analogous in a rotational picture? So I'm just going to answer that for you. It's called rotational inertia. You might also hear it being referred to as moment of inertia. Those are synonymous, and it's basically the thing that you have to overcome in order to accelerate something, right? So in the linear picture, I have to overcome, the more mass I have, the more force I need to achieve a certain acceleration, right? Similarly, in the rotational picture, the greater my rotational inertia, the more something I need that I haven't yet defined that will allow that thing to rotate. Okay, so rotational inertia or moment of inertia depends not just on the mass of something, but how that mass is distributed. Okay, so if you wanted to compute, say you wanted to compute what's the rotational inertia of this clicker, you would have to say, okay, well, first of all, where are you rotating it? About what axis? Are you rotating it this way? Are you rotating it this way? And define your axis. Maybe it's like this. Then, with respect to that rotational axis, you would need to add up the mass, little chunk of mass, times the distance squared to that rotational axis for every little chunk that makes up this clicker. In other words, this sum for an extended object is really like an integral. Okay, you'd have to integrate all of those little bits of matter and their distance squared from the rotational axis. Okay, so that's a big job. A lot of times we don't actually need to compute that, because if it's a regularly shaped object, then these answers have been worked out. Somebody has done that integration for us and compiled it on some sort of a chart or a table that tells me about regularly shaped objects and what their moments of inertia are, depending on what axis I rotate the object about. So for instance, if I have a chunk of wood that's a rectangular block, those of you who are in Calculus 2, and you may have done some of these kind of two-dimensional, three-dimensional integrals, maybe you could infer that I could come up with some formula that would describe that when I perform this integral. And so somebody has already done that for me, and they've said, okay, if you have a slab and you rotate it about this axis, then the moment of inertia could be found by taking, I know it's kind of small for those in the back, but this says the mass of the object times the width squared plus the length squared divided by 12. So, you know, the longer this thing is, the larger its moment of inertia is going to be, right? Okay. Or if I have something that's like a hoop, I could, again, it depends where I rotate this thing. I could rotate it like this, or I could rotate it like a wheel, right? And those will give me different moments of inertia. If I refer to my chart for a hoop that's rotating like a wheel about this axis, then it's just the mass times the radius of the hoop squared. But if I rotate it about this axis, like so, then you take that and you divide by 2. Okay, so maybe your problem will say a hoop of 3 inches radius and a mass of, I don't know, 0.6 kilograms or something. And then you would plug those into that formula and you would have your moment of inertia. Okay, so those are some examples of regularly shaped objects. And so from this formula, you can infer what the units of moment of inertia or rotational inertia need to be. They must be not just a kilogram like we had in the linear picture with Newton's second law. Well, now I've got a kilogram times a meter squared, right? Okay. Now, what if I wanted to rotate something about a different axis than what's in the chart? Any baseball players out there? Nobody plays baseball? Somebody played Little League, right? How about softball players? Okay, you're a baseball player? Okay, so you don't generally rotate your baseball bat about the middle, right? Or like this, right? You're holding it at the end. Or maybe if it's too big, you might choke up a little. But either way, you're not rotating it about an axis that's on this chart. We can figure out what the moment of inertia should be for rotation about a different axis if we go ahead and find the rotational inertia through the center of mass, and then we add something to it. We add a term to it that describes the mass times the distance squared that exists beyond that, right? So that's called the parallel axis theorem. And anytime you have an axis that's parallel to the one through the center of mass, you can do this. Okay, now, when you rotate something, so I've sort of alluded to this, right? Question. Which side is H? Oh, I guess because I want to rotate over here, not over here. So there should be like an X here that indicates like where I'm actually rotating. Does that make sense? So I've alluded to this, that the larger the moment of inertia something has, I should say, the harder it is to rotate. So I've got 2 sticks here that have the same mass, but the mass is distributed differently, so that even if I rotate them both about the center, it turns out that one is going to be easier to rotate than the other. Okay? And that has to do with the fact that the mass is distributed differently, so the moment of inertia of one is larger than the other. Okay? So be careful not to bonk each other, but I'm going to go ahead and pass these through the aisles, and you can do a little experiment and you can decide which one you think has a greater moment of inertia. Okay? Meanwhile, the rest of us can do this. How many have done this in their high school physics class? Okay, so you're not allowed to guess then what the answer is if you've already done this. So I've got a hoop and a solid disc, right? Now, according to what we already know, things should fall at the same rate near the surface of the Earth, regardless of their mass. So let's not focus too much on the mass per se, but let's focus on the fact that they are the same radius, but that mass is distributed differently. Right here, it's concentrated in the exterior. Here, it's spread all about. And remember that the formula for moment of inertia, just generally speaking, is I equals the sum of MIRI squared. So maybe you can use that to develop a little intuition about which one gravity will have an easier time rotating down this inclined plane. Okay, so how many are team hoop? How many are team disc? It's pretty split. Let's see who wins. All right, here we go. Look like team disc wins. You can't win them all, right? Now, if we go back, we can try to understand that in terms of these formulas. So remember that the hoop is mr squared. What is the disc like? Well, the disc is sort of like a cylinder that's just squashed, right? And the cylinder is mr squared over 2. So it has a smaller moment of inertia. Therefore, it's easier for whatever is being applied to it, I haven't defined that yet, to accelerate it. But it has something to do with gravity. Okay? Now, when you were taking your exam, poor Esther, the Wonder Pig, had to slide down a ramp, right? And you had to determine something about her velocity at the end, because she was basically transforming potential energy into kinetic energy. If I roll something down a ramp, as opposed to sliding it down a ramp, I kind of know that now it's got some energy of motion too, right? But it's a little awkward to think about 1/2 mv squared when I'm rotating. So is there a rotational analog to that? The answer is yes. Kinetic energy can also be expressed in terms of rotational kinetic energy. If something is rotating, it's got energy of motion associated with that rotation. And this formula is what you might naively guess. Now that you know that rotational inertia is the angular analog to mass, and you already knew that angular velocity omega is the angular analog to linear velocity v, then you might guess instead of 1/2 mv squared, I might have 1/2 I omega squared. And that is exactly what I have. Okay? And the work kinetic energy theorem can apply to this as well, so that you have, if you have work being done, that should amount to some change of kinetic energy. And if I do some work to rotate something, I can change its rotational kinetic energy in the same way that I would have in the linear picture. Okay, so I think this is relevant to one of your homework problems. All right. But I feel like I've been leading up to this question of Newton's second law for rotation. We're building the understanding. We've got a rotational analog to mass, but okay, let's get to the point here. If I go to this formula, then I might guess that the right-hand side, instead of mass, I'm going to use I for rotational inertia. And instead of linear acceleration, I'll use alpha for angular acceleration. But then what is the left-hand side going to be? It can't quite be forces because the unit is wrong, right? Because moment of inertia is kilogram times meter squared. So what could I have instead? Any ideas on what belongs on the left-hand side for my angular analog to Newton's second law? Torque. Very good. So torque. So we might have an everyday sense of what torque means, but let's go ahead and define it. So torque is, naively, you could think about it as the ability to rotate something. And it has to do not just with the force that's applied, but two things: where it's applied and what angle it's applied at. So if I go over to this door and I push it in the middle, I'm not going to get very much torque if this is my rotational axis, right? Okay, if I exert a certain amount of force that close to my rotational axis, I don't actually get a lot of torque. But if I increase my lever arm and go over here, that far away from the rotational axis of the hinges, the same amount of force is much more effective, right? If I push at some weird angle, though, that's not really good either, okay? So all these ingredients come together. By the way, that's why handles are on the ends of doors rather than in the middle, unless you're a hobbit, right? But typically, they're at the ends of the doors. All these ingredients come together for this quantity called torque, which we indicate with the Greek symbol tau. It is a vector because force is a vector, and this lever arm R is also a vector because it cares about direction, okay? And so remember back at the beginning of the semester, I introduced vector products, and I said, okay, there's the dot product and the cross product, but we don't need to worry about it that much until we get to torque. Well, we're finally there, okay? The day has come where we now have to think about cross products. But luckily for you, you won't need to compute them quite so painfully. In most cases, what you'll need to do is simply figure out what is the magnitude of the torque, and then I'm going to use my right-hand rule to determine the direction of the torque. So the magnitude of the torque then is the product of R times F times sine of the angle between them. That's my magnitude of my torque. From either of these equations, I can deduce what the units of torque have to be. They have to be a unit of a force times a unit of length, right? So a Newton times a meter. All right? So this is why, how many of you have had to put together IKEA furniture with those obnoxious little Allen wrenches, right? You know, if you take the end where it's just the little end and you try to spin it, it might be convenient so you're not knocking it into all of the small stuff that it's not very well designed for. But then after a certain tightening, you're like, I can't do it. So you flip it the other way because why? It has a longer lever arm and you can get more torque. Okay? Well, the longer the wrench, the better the torque. Now, what about the direction of the torque? Typically, it amounts to a sign, a positive sign or a negative sign. How will I determine that? Well, you can figure it out in a couple of different ways. You can use the whole lefty-loosey, righty-tighty idea. What do I mean by that? So picture that you're screwing some drywall screw into your dorm wall, even though maybe it's not allowed, but you really need to hang up a picture of Esther the Wonder Cow, you know, and her foray into skydiving, right? So you're screwing this thing into the wall. How do I know if my torque is going into the wall or out of the wall? Well, you kind of intuitively know, righty-tighty, right? So I can use that principle, and I could imagine my thumb going in the direction of the torque, the radius of the screwdriver going like this, and then my fingers curling in the direction that I'm turning the thing in. I'm applying the force like this, right? That would give me a negative torque. Now, if I wanted to unscrew that, then I really would want to apply the force this way. Now, you might not actually flip your hand like this, but for our purposes, that's kind of what you want to do because you want your thumb to somehow point in the direction of the torque. So if you go counterclockwise, lefty-loosey, then your torque would be out of the wall, right? Another way you can think about it is with the right-hand rule. If your thumb points in the direction of the lever arm and your finger points in the direction of the force, then the torque is like this, in the direction of your middle finger. So you can pick whichever right-hand rule you like. You can practice different ones and decide what's best for you. But another way to think about it is, you know, which direction are things going to rotate? And maybe that'll help. Okay, so here we go. We figured it out. This must be the rotational analog of Newton's second law. We replaced mass with moment of inertia. We replaced angular acceleration with alpha. And we replaced force with this idea of torque. Just like in the linear picture, this has to be the net torque. So if there's more than one kind of torque on something, then I've got to add or subtract that accordingly. Before I get there, let's do another demo where I show you that this works. So here I have an object that I can rotate by applying a torque through this connected mass, right? And it will rotate the thing once I let go, okay? I can distribute the mass differently on here. I can keep it near the axis of rotation, which would give me a small moment of inertia because the R in that formula is very small, right? In mr squared. Or I could spread it out. Now it's more like the hoop, right? Where things are out on the ends and the R, most of the mass is out here. So the R is much larger in mr squared. So in that case, the moment of inertia is going to be greater and it should be harder to rotate. Like one of those sticks that's going around is harder to rotate. So let's see if we can see that play out. Give me a second while I change the screen. Okay, so the computer's going to collect some data. It doesn't unfortunately show me the angular acceleration alpha, but it does show me the angle theta at the bottom and the velocity in radians per second at the top. So it should go through more rotations more quickly if it's got a large angular acceleration, right? If it's got a small angular acceleration, then it'll take longer to go through the same amount of rotations. So let's take the case where the weight is distributed close to the center of the axis. The moment of inertia is small. And so I expect for a certain amount of torque that I should get a pretty fast acceleration. All right, let's see if we get something that accelerates pretty rapidly when I do that. Okay. Eventually it'll run out of steam and go the other way. Okay, and it changed direction there, right? Okay, so what did we see? We saw that, so in a time of 10 seconds, it's gone 30 radians. You see that? Right, so now let's try the same thing, only let's distribute the mass differently so that it's spread out to near the ends, making the moment of inertia larger. And so now, according to the second law for rotation, it should, for the same amount of torque, not achieve quite the same amount of angular acceleration, so that it should take longer to go through that same amount of angles. Let's see if that's the case. You can probably qualitatively see that happening as well. Okay, let's not worry so much about the sign here, but you can see, I think, that in that same 10 seconds, it only went from a little more than 40 to 50. So like 12 maybe radians rather than 30 radians. Okay? So we have verified that Newton's second law for rotation actually works. Now, I did gloss over some things here because remember that it's net torque. In reality, there's probably some friction here that is applying a torque against that, but we ignored that for our purposes right now. So, when we say net torque, by the way, things aren't always rotating, right? Remember at the playground, those seesaw things? Did you ever do a thing with your friend where you got in just the right distance from the fulcrum of that thing so that it just balanced? Anybody ever do that? Okay. And it just balanced. Instead of rotating this way or this way, it was just imbalance, right? At least until your nasty friend jumped off the end and sent you flying, right? That was always the worst. But until that happened, you had no angular acceleration. So it could be the case that this goes to 0 if alpha is equal to 0, right? In other words, you could have a state of torque equilibrium. And in fact, we're going to define something called static equilibrium, which is the case when you have no net torque and no net force. In other words, your torque on the seesaw balanced equal and opposite with your friend's torque on the seesaw. You didn't need to be the same mass because with torque, the lever arm matters, right? So if you were a little punier, you could sit closer to the fulcrum and achieve the same torque. Okay? But so long as those things are in balance, both the force and the torque, then you're in what we would call a state of static equilibrium. So this balance here is showing you a state of static equilibrium. This climber is also in a state of static equilibrium. Okay? And I think I would like to do an example that illustrates that. But so far, are there any questions about the rotational analog of Newton's second law? Okay, so as I've been doing, because it's fun, I came up with an acronym to help us think about how to approach these problems. So you might be feeling a little down after taking a test, or maybe you feel great. I hope you feel great. But if you feel down, just remember that you're strong. Okay, this person is pumping iron. They've got, they're applying a torque, right? The lever arm is their forearm. Okay, you can do this. You're strong. Okay, sometimes though, you will need both the linear Newton's second law and the angular second law. Okay. So how am I going to do this? First of all, I may need to draw two diagrams, a regular free body diagram like I'm used to drawing, and something I call an extended free body diagram. Why do we need an extended free body diagram? Well, it matters where I'm applying the force in terms of the torque, right? So I have to actually depict that on the extended body that I'm considering. Once you've done that, remember when you were doing inclined plane problems with Newton's second law, you could use a tilted coordinate system because it made the math a little bit easier. I didn't have to resolve as many things into components. We can do something analogous in the rotational picture, and that is that we can choose our rotational axis in a way that makes the math easier, even if it's not necessarily rotating about that axis. Let me choose one so that, well, let's say that I choose this as my rotational axis and I put a force right there at the rotational axis. Then what is the lever arm? It's just 0, right? And if torque is force times lever arm, then it's force times 0. So that torque doesn't need to be included in my net torque sum. So that'll make my math easier. So you want to choose the origin for your rotational axis where it's convenient. And sometimes that takes a little bit of developing intuition about these things. Sometimes you might need to resolve your forces into components if they're off at certain angles with respect to the lever arm or your origin. So you might still need to do that. Then you're going to have to quantify both Newton's second law and Newton's second law for rotation. So that could involve X and Y for Newton's second law, and then one equation for Newton's second law for rotation where I just make sure I put the right sign in for my torques. And so that could be 1, 2, 3 equations. So up to 3 unknowns might be included. Okay, once I've fleshed out both of those laws, then as I've become accustomed to doing for these systems of equations, two equations, 2 unknowns, 3 equations, 3 unknowns, by this point now, you know the drill. I've got to use some substitutions perhaps and plug those into another equation in order to solve for the system of equations. And then I bet you guys are smart enough to guess what the E in torque stands for. Evaluate or examine your answer for sensibility. Okay? All right, so let's go ahead and put those practices into motion with an example. And you'll have to bear with me that the formatting on these slides sort of went to pot here. So I'm going to try to get it working for you. We're going to consider that climber that we just saw on the title slide. And we're going to start by drawing both a free body diagram and an extended free body diagram for this climber. But before we do that, how many forces do I need to include? Let's name some of the forces. Let's do this together. What's a force I'm going to need to include for this climber? Weight. What else? Tension. What else? Normal force. Yes. And there's one more. Friction. Exactly. So I need 1, 2, 3, 4 forces on my free body diagram. So the rope is providing tension. The earth is exerting the force of gravity on the climber. The rock face is exerting a normal force perpendicular to this rock face. And what's preventing the guy's feet from sliding downward? Static friction, right? Otherwise, you know, if you had sort of slippery shoes on, which wouldn't be a great idea, then, you know, static friction wouldn't be strong enough and your feet would slide. Okay? So here's the extended free body diagram that I've drawn. And I've tried to depict where these forces are being applied. The tension force is being applied here, a distance of 1.06 meters from his feet. And I'm going to go ahead and assume that that is also his center of mass, and we'll put the weight force right there. The normal force is exerting a force perpendicular to the rock face, and the static friction force is up, because how would his feet slide? Down, right? So the static friction must be exerting a force up. I've also defined some angles here. This one between the rock face and the rope, I'm calling phi. This one between the rock face and his feet, I'm calling theta. And this distance from his feet to where he's tied in, we're going to call L. Okay, and that L is given to me, by the way, in the problem statement. Okay, now, if I wanted to take all of those same forces and put them on a regular free body diagram, then I just boil it down to his center of mass, and I draw all of those forces as though they're coming out of the center of mass. That will help me when I use Newton's second law in the linear picture. For the rotational picture, I need this. For the linear picture, I really don't want to have to think about where it's being applied. I want to just put them all in the same place. So I can draw the tension here. I can draw the normal force here. I can draw the friction force here. And I can draw the weight force here. And that's my regular free body diagram. So I've done the first step in my acronym, 2 diagrams, free body diagram and extended free body diagram. Okay. The next step is defining my origin in a smart way. it may not be immediately apparent how to do this, but here's some things to think about. First of all, we want to know something about the static friction coefficient, okay? And we're given a lot of information, but we aren't given what this normal force is, and we're not given what this tension force is, okay? And so I might need to think about making some substitutions for tension. So I've defined my origin here to eliminate the unknown normal force. How have I eliminated that? Well, if that's my axis of rotation, then my lever arm for the normal force is 0. Okay? And so the torque being exerted there is also 0. Normal force times 0 equals 0. So I've defined my rotational axis there. If it's not clear that that's the best spot, that's okay. This problem would work if you defined it somewhere else. And as we go through the next steps, I think it'll be a little bit clearer why I chose that spot. Okay, so I've done T and O. So the next step then would be to resolve things into components and apply the different laws. But I'm going to go ahead and jump right into Newton's second law like we would normally apply it. So let's go back to the regular free body diagram. It looks something like this. The tension, the normal force, the weight force, and the friction force. And even before we introduced rotation, you would have been able to probably come up with these equations for Newton's second law. If you just saw that free body diagram and I gave you that free body diagram, I'd say, okay, go ahead, tell me what the sum of the forces is in the x direction and the y direction. And you could probably do that. Let's go ahead and do that. So the sum of the forces in the x direction is going to include the normal force in the positive x direction. And then I've got a component of the tension force. Does everybody see that? Because the tension's going off to an angle. So there's some component of the tension force like this, right? And so I've got to subtract that off since it's pointing in the negative x direction, negative tension in the x direction. Okay? That all has to add up to 0, which means then that the normal force has to equal this component of the tension in the x direction. Let's see if we can figure out what that component is. So, well, I'll get back to that. Let's go ahead and sum the forces in the y direction. In the y direction, I've got the friction force in the positive y direction. I've got the weight force in the negative y direction. And I've also got the component of the tension force in the positive y direction, right? This is Ty, this is Tx. All of that also has to add up to 0. Okay? So, if I take this second equation, actually let's go back to the first equation, and let's look at where this thing is. So, I argue that this is going to be T times sine of phi. Right? Because why? Like, think about this as a right triangle. If I go ahead and extend this over, this component is opposite the angle phi that was given to me. So even though x is normally associated with cosine, remember, you've got to look at your reference triangle to make sure of that. In this case, that component is opposite of the given angle phi. So it's T sine of phi. All right, let's flesh this out a little. We know that in a maximally static friction case, that the static friction force would be the coefficient of static friction times the normal force. And the y component then must be the side that's adjacent to that given angle phi. So it's the cosine of phi. Now, None of this is entirely new to you, right? You would have done stuff like this, even before today. So the next step I want to say is, well, I don't know anything about the normal force. Maybe I can at least express it in terms of the tension by making a substitution in there. Okay, then instead of two unknowns, the normal force and the tension force, at least then I just have one unknown, the tension force. Okay, so let's, instead of calling this the normal force, let's call it T sine of phi. All of that has to add up to 0. All right, everybody with me so far? So that was the quote unquote easy part. Not that it's easy. Don't mean to say that, but it's at least familiar to us, right? We've done this kind of thing before. Now we venture into the unknown where we're going to apply Newton's second law for rotation. Okay. So for the next slide, what we want is to sum up torques rather than forces. Okay. So if I take this to be my axis of rotation, I want to find the torque about that axis, the net torque. But the static friction force is right at the axis of rotation, as is the normal force. So both of their lever arms are 0. They do not need to be included in this sum. Instead, I only have two forces that exert a torque about this axis of rotation, one due to gravity and one due to the tension force. So remember that torque is force crossed with the lever arm. So the force of gravity crossed with its distance to this axis of rotation, plus the torque crossed with its distance to the axis of rotation. So I've just written that very generically, but let's go ahead and plug it in terms of what's been given to me in the problem. So in the problem, I know that both the torque, the tension, and the weight force are a distance L from this axis of rotation. So this magnitude of the distance becomes L. And the magnitude of the forces are Fg and T. And then we need the sine of the angle in between those two things, which we'll talk about in just a second. But what about this minus sign? How did I know that this one should be plus and this one should be minus? Yes, I like what you said. I thought it was going to go sideways, but you said it right. A temptation might be to think, well, the force of gravity acts down in the negative direction. Nope, that's not why. The reason why is what he just said, which is that it would cause, if I didn't have that tension there, and I just imagine what would happen to the rotation about that red dot would be clockwise, right? So the rope just broke, it would go this way. And that clockwise direction is associated with a negative sign, remember? So if you're not too schooled on the right-hand rule yet, just think about it this way. If that was the only torque being exerted, ignore all other torques, what direction would it rotate? If it's clockwise, it's negative. If it's counterclockwise, it's positive, right? And so the tension must be the opposite, right? If I could eliminate gravity and it was only tension, it would rotate counterclockwise. Okay, so that's why we have two different signs here, negative and positive. Everybody follow that? Okay, so then now it remains only to define what these angles are. What is the angle between the force of gravity and this lever arm? And what is the angle between the tension force and that same lever arm? So this is my R that I'm considering. For gravity, does everybody see that this angle here for gravity is the same as this angle down here? Because they are alternate interior angles. So they're equivalent, right? For this one, it's a little trickier because that angle is this. that whole thing. But I can figure that out, right? Because I know that phi plus theta plus whatever that angle is has to add up to 180. Exactly. So if I take 180 and I subtract off phi and theta, then that'll give me that angle. In this case, 40, 30. I can figure out what the rest is. So, what that gives me then is minus mg L sine of phi plus TL sine of 180 minus phi minus theta. Okay? So then, the object of the game is to make some substitutions. We know this. We have another equation on the other side. What we should be able to do is ultimately eliminate an unknown and solve for that coefficient of friction. I apologize that we're running out of time, but you can come and talk to me if you have a few after class. But that's how we would go about solving one of these net torque problems. Have a great weekend. I will see you next week.